All right, so we're going to do our challenge question about the hydrogen gas being used in the water-gas shift reaction. So this reaction is used to produce hydrogen gas that can be used in hydrogen fuel cells and has the benefit of using up poisonous carbon monoxide gas that can be produced in the proton exchange membrane fuel cell. So this has a bit of a redox tie-in, but we're going to worry about this in terms of equilibrium. So it says, write the equilibrium law expression for the water-gas shift reaction. So the equilibrium law is going to be equal to the product molar concentrations raised to the power of their coefficients, in this case 1, divided by the reactants, that's carbon monoxide, and water vapor. Now it's water vapor. If this was water liquid, it would not get included in this equation, but water vapor can have a molar concentration. So could an aqueous water molecule. So if you dissolve water in alcohol or something like that. Not aqueous water molecule. If you have water dissolved in like alcohol, it also can have a concentration. So it says here for question 2, what is the equilibrium constant if a 2-liter container at 150 degrees Celsius has 18 grams of water vapor and 38 grams of carbon monoxide added to it? And so what we're going to need to calculate is the molar concentration of water vapor to do that. So the mass of water in this case is 18.0 grams. The molar mass of water is 18.02 gram per mole, and the volume of the container is 2.0 liters. So the number of moles is going to equal mass over molar mass. So we've got 18.0 grams divided by 18.02 gram per mole. And that's going to give us 0.999 mole. And then the concentration is going to be that molar amount, so 0.999 mole, divided by the number of liters, which is 2.00 liters. So this is 0.499 mole per liter. So that's going to be our initial concentration of water vapor. And we can do the same thing for carbon dioxide. So I've got a mass of carbon dioxide is 38.0 grams. The molar mass of carbon monoxide is going to be 38.01 gram per mole. And again, the volume is 2.0 liters because it's the same container. So we can calculate its concentration. I'm going to take my 38 grams divided by 38.01 gives me the number of moles divided by 2 liters. So we have this, the concentration for this is 0 point, and this is going to round off to 500 mole per liter. So we have our two concentrations, and I've built the table here. Please ignore this. I calculated the molar concentration for carbon dioxide previously. Our carbon monoxide, I'll just fold it over and then we don't need to worry about it. Our carbon monoxide is 0.500 mole per liter, and our water is 0.499 mole per liter. And it's telling us that the hydrogen gas collected at the end is 0.452 mole per liter. And then it wants us to calculate the Kc, and we've got that expression over here. So this is going from 0. We start with an empty container and add those chemicals. So this is plus 0.452 mole per liter. This will be plus 0.452 mole per liter times 1 over 1. I get one of these to one of these. So it's also going to be 0.452 mole per liter. And then I'm going to use up the reactant. So minus 0.452 mole per liter times 1 to 1, because it's a 1-to-1 ratio. So minus 0.452. This will be the same thing, minus 0.452. And I calculated that by using the coefficients. In this case, it's 1-to-1, so it's nice and easy. So if I take 0.500 minus 0.452, the equilibrium concentration of this is 0.048. And this one, because we said it was 0.499, this is going to be 0.047. And so I can fill this in. This is going to be 0.452 mole per liter times 0.452 mole per liter. I'm ignoring my units. I would dock me marks for that. 0.048 mole per liter. And then times 0.047 mole per liter. And this should give me my equilibrium concentration. So my equilibrium constant here is going to be 90.6 is my equilibrium constant at 150 degrees Celsius. So my Kc equals 90.6 at 150 degrees Celsius. It says in question 3, the equilibrium constant for the water gas shift at 500 degrees Celsius is 7.8. What is the equilibrium concentration of all the reactants and products if a starting concentration of 2 mole per liter of both carbon monoxide and water vapor are reacted? So I've set up an